So in the book, they go over a couple of examples. This is actually very useful, but perhaps the examples covered in the book are not good enough at covering more exotic possibilities that we may actually encounter later on in the course. Remember, the principle that we ended with is that or the observation is that most time, oftentimes when you thought about subsets of real numbers, you tend to think about intervals that is not going to be the most general kind of object that we'll be handling in analysis in general. So sets can be defined by the properties of the numbers that belong to that set, and they can be very wild in principle. So let's start looking at what they give here as example 1.3.3. So they let A be the set of numbers 1 over n, where n belongs to the natural numbers. Okay, so this set can also be written as 1, set consisting of 1, 1/2, 1/3, 1/4, 1/5, and etc. This set is infinite. It has infinitely many numbers, and it can be seen. If you look at the real line, this is 0 and this is 1. Then the set is clearly bounded from above and below. So 1, then we have 1/2, then 1/3, and then subsequently smaller numbers to the left of 1/3, but never actually touching 0. So the set A is the union of these singletons. Okay. And so naturally A is bounded from above by actually any natural number. Right. And including 1. At the same time, so because numbers in A are negative, A is also bounded from below. So according to the least upper bound property and the greatest lower bound property, we know that then that A has a supremum and an infimum. So what are these? The supremum of A, which is denoted sub A, is equal to what? This is the first question. And then the second question is that the infimum A denoted if of A is equal to what? What are the candidates that we have here? Of course, A is bounded by any natural number greater than or equal to 1, and 1 is actually in the set. So it cannot be anything, least upper bound cannot be smaller than 1 because 1 is in the set. And you see that if you pick any other number, by any number greater than 1, then 1 is going to be, of course, less than that number. And it's going to, and all upper bounds have to be greater than 1. So that will imply that, that would imply that 1 would have to be the supremum. On the other hand, 1 also belongs to the set. If we look at the greatest lower bound, what is the natural candidate for a greatest lower bound? We have to arrive at the conclusion that it would have to be 0. Because when we let n go to infinity, 1 over n gets smaller and smaller. And in fact, no matter how small a number is, in a number greater than 0 is, you will always find a number n such that 1 over n is smaller than that given number. Well, again, it's the Archimedean property showing up again. But then that would mean that no positive number can be a lower bound. Okay, so no positive number can be a lower bound, and so 0 is certainly a lower bound, and because all these numbers are positive, and no positive number can be a lower bound, so that means 0 has to be the least upper bound. So what we've said here, very informally, is something that we'll complete in detail in a little while. Okay. So comment. So first. Let's show that one is indeed least upper bound. So we must ask ourselves two questions. Remember, there are two properties. So is one an upper bound? Yes. For every n in n, 1 over n is less than or equal to 1. Remember, this is just equivalent to saying that n is greater than or equal to 1, just by multiplying by, since you know that this is true, n is greater than or equal to 1 for any n in n, you may divide by n, and you get that 1 over n is less than or equal to 1. And that comes from one of the properties we mentioned at the beginning of this module, that we'll assume that it's right. So whenever you multiply an inequality by a positive number, you keep the same ordering in the inequality, okay, on both sides. So yeah, this is true. So 1 is an upper bound. It bounds 1 over n for every n in n. And now, is it at least upper bound? So here, of course, we've already shown that this is a upper bound, but is it at least upper bound? If a number b is an upper bound for a, then it must satisfy that b is greater than or equal to 1 over n for every n in n. And here I want you to pay attention to this property here, or this statement. So if we are looking at it from the perspective of testing whether something that we're saying is true or not, what we're saying here is that b is greater than or equal to 1 over n for every n in n, and that means that no matter what n I put in here, the statement b greater than or equal to 1 over n must be true. Okay, so but that allows me to test for n equals 1, and that's what I mean in what will mean then in the future when I say in particular it must be true that b is greater than or equal to 1 over 1. 1 is in n, and is equal to 1. So what we've concluded is that then b, our upper bound for a, must be greater than or equal to 1. And this is the second property that we need to show when we show something, when we claim that something is a least upper bound. So we have, so in sum, that a, or just put it in quotes, or that 1 is an upper bound for a, and second property is that if b is an upper bound for a, then b is greater than or equal to 1. And these two things together when 1 is the least upper bound for supremum of A. So coming back to the notation, so we can use a notation. So let me just use this. So we write supremum of A is equal to 1. So let's go back. So we had the set A of all the numbers of the form 1 over n, where n was a natural number, and we were trying to show that 1 is the supremum or the least upper bound. We first show that 1 was an upper bound. This is what we proved in here. So we took any element in the set and we proved that 1 was greater than or equal to each one of the elements in this set. And then we showed that it was the least upper bound, meaning that if we picked any other upper bound, then B had to be greater than 1, which is what we arrived at in here. And combining these two things together, because of the definition of the least upper bound, we concluded then that the supremum of A is in fact equal to 1. So what about the infimum? We will show in a while, in a little while, that the infimum of A is equal to 0. Okay, as I said, this could be deduced from the Archimedean property, but the observation is the following. So suppose, so this is not actually a proof, but we know that 0 is a lower bound. Yeah, we know that one for sure. Now the question is, can there be any lower bound that can be greater than 0? So suppose epsilon greater than 0 is a lower bound. In fact, we don't even need to assume that this is a lower bound. We can just pick or choose So let's just let epsilon be some number greater than 0. And this is the part I was referring to. We know that no matter how small epsilon is, we know epsilon greater than 0 is, there exists n in n such that n epsilon will be greater than 1. And this in turn is equivalent to saying that epsilon is greater than 1 over n. Okay? But what does this mean? What does this mean? If epsilon is greater than 1 over n, then it can certainly not be, it cannot be the lower bound. Means epsilon cannot be a lower bound because epsilon would have to be greater than or less than or equal to 1 over n for every n in n. So, but here we found a number n such that 1 over n is less than epsilon. So epsilon cannot be the least, the greatest lower bound because it's not even a lower bound. And here's the thing. So why do we know that n epsilon is greater than 1? For at least one n. In fact, for infinitely many. And that's boils down basically to looking at the Archimedean property, which is what we're gonna see and discuss in a little while.